All right, so next up is Stu Carter. So Stu's been pretty involved here maybe for the last few years. I think we first met at the Wireless at BT Symposium a number of years ago. And Stu has a lot of experience using good radio in a DoD context. And he's going to share some of his insights now. So with that, I will... Actually, we have a small problem that the slides are not showing up.
So, right?
Oh, it might actually hit the coordinate right down there. That's probably my fault because I may or may not have kicked it.
Tell you what.
Oh, you're up. All right, we're all set.
Okay, so I really enjoyed the previous couple of presentations. My dissertation work was in applying information theory to evolutionary computation-based machine learning, so that distributed learning algorithms for doing network coding is something I really want to dive in after I get back from the conference. Unfortunately, I'm not wearing my Dilbert hat today. I'm wearing my pointy-haired boss hat. So I'm giving essentially an extended pitch for work that's going on at the Air Force Research Laboratory's Information Directorate up in Rome, New York, at the former Curtis Air Force Base. And the big long disclaimer is because I actually pushed this through the Public Affairs Office. And I did that last year when I was supposed to present this, and sadly, on the day before the conference began, I went out and did a mud run, and on one of the last obstacles, I broke my leg in 3 places. So I did not present this last year. Rather than go through the agony of push slides to the Public Affairs Office again, I brought last year's slides, but I will bring them a little up to date as I go through them. So, for those of you who haven't worked in the military comms world, it's a lot like the commercial comms world, but in some respects even worse. We go places where there's not much infrastructure, we move around a lot. We have not only script kiddies and economically motivated people trying to intrude into our systems, we have, nation states and other actors. Our links tend to have low data rates, long latencies, high error rates, and the thing that people don't realize at first going in is actually the biggest problem is rapid variation in link characteristics. And so, especially when you get up into the the transport layer, most transport layer protocols like TCP have a real problem with variation in the underlying links. So anyway, we have all kinds of problems, and so we hope to use the same technologies that everybody else is hoping to use to solve them. We have some big test beds, really big. And so they've got diverse emitters, they have diverse purposes for which we're using them, whether it's electromagnetic compatibility testing or what have you. The big test beds involve anything from inside of a large anechoic chamber to outdoor ranges to distributed ranges. Now there's some things that these guys need, and they know they need some of them, and if they don't get them, they need some of the others. So for instance, iRig time. They all know that they need iRig time. What in many cases they haven't realized is that for some work where phase coherency across distributed sensors matters, they need things like White Rabbit. Now, if you haven't run across White Rabbit, it is a further precision enhancement to the precision time protocol of IEEE 1588, which is a replacement for our old friend NTP. It was developed mostly by the European particle accelerator folks. I mean, when you want to measure the time that neutrinos take to get from Switzerland to Italy and not accidentally think that they went faster than C, you need White Rabbit. So there's a couple of other things that we're really focused on standardizing on in our work. VITA 49, which underlies the UHD that you all use. LXI, so for those of you who remember the old Hewlett-Packard interface bus, and then GPIB, and then all the different incarnations that went through, the latest one is LXI, LAN extensions for instrumentation. We're trying to standardize on using LXI to orchestrate our whole test environment. And so one of the things that implies is we would like for software-defined radios to be triggerable over LXI. So we're probably going to create a couple of new radio blocks to facilitate treating the SDR as the piece of test equipment that we sell it as, so that we can avoid FCC type acceptance issues. Now, by big chamber, I don't know if you can see this one very well, but that is not a model airplane. That is not a UAV. That is an F-15. And it is hanging inside the world's largest anechoic chamber out at Edwards Air Force Base in California. And they can accommodate aircraft bigger than that. They've had a C-17 cargo plane in there, okay? So pretty nifty. Now this is right near my house. Yes, that's what it looks like on a stick. And I've seen some very interesting things up on that stick. We refer to it as the upside down Air Force. And you might wonder, why in the world would somebody put a plane upside down? Well, because when you want to study antenna patterns and things like that, typically you're interested in what airplanes do when they're at altitude. But if you don't want to burn fuel, which is very, very expensive, how do you simulate being at altitude? Well, just turn the plane upside down, and now you've got infinite space above it, as if it were at a high altitude. So that's one of Air Force Research Laboratory's facilities in upstate New York. That stick that I just showed you with the vehicle on it is on top of one of these 4 hills. There are actually 4 hills there, so we can have antennas sitting on one hilltop, aiming across the valley, looking at an aircraft on a stick on another hilltop. And what makes this environment really nice is all my neighbors are Amish. This is a really radio quiet place to do your testing. And also, if you generate any interference, interfere with who? No one's going to know. This is another one of our outdoor ranges. This is in a little town called Stockbridge, New York. The dashed and dotted and solid lines are roads of various grades. The worst grade roads are ones that you better have a four-wheeler or you're not going to get through. And they've actually got a little runway there. And they fly what they call small unmanned aerial systems, SUASs, out of there. Small means under 55 pounds. And a 55-pound UAV is, in my book, still a pretty big UAV. Some of these are fixed wing, a lot of them these days are multi-rotors. And all of these little yellow dots are concrete pads with big metal box military shelters with 4 hard points on the corners of the pad and 220 volt power and more fiber than God, and towers, antenna towers. And so this is this big outdoor distributed test bed for doing things in the intersection of RF and cyber, whatever the heck that means, and unmanned aerial systems. And it's as of yet underutilized. So if you have things that make sense to do there, if you already have contacts at the Air Force Research Laboratory in Rome, talk to them. If you don't have contacts there, talk to me. So one of the issues we face is complex waveforms. Now, in DoD parlance, if you're familiar with like the SCA and so on, waveform means a lot more than the little squiggles that I think a waveform is. LTE is a big focus right now because some of the adversaries use it to make things blow up at inappropriate times. And also because it's the sort of thing that we might want to deploy ourselves. For instance, on UAV, why not fly an LTE base station around in theater to provide connectivity to low-cost, highly capable, small mobile devices? Another DoD thing is UAS, the Multi-User Objective System, which is the latest generation of DoD SATCOM, and I have a couple more slides on that later. Another issue that we confront is we have what I'll call empirically observed waveforms. Ones for which there is not an open standard specification document to which we can refer, but that may be important to us. And so the simplest thing you can do is use a digital RF memory to just record it and play it back later. But that's no good if this waveform normally carries some kind of modulation that is likely to be dynamic, like, for instance, navigational information for an aircraft or some other form of telemetry. The RF will not be realistic if you simply play back and record. So you can see, obviously, the utility that something like the radio has for generating those sorts of emissions in a chamber. And here's an example with MUAS. This is the actual MUAS system architecture. There's one network management facility, there's 2 satellite control facilities, there are 2 switching facilities, there are 4 radio access facilities, and from a mobile user terminal, you go up over UHF, because UHF is something that can penetrate foliage and it's relatively easy to make a mobile UHF terminal. Once it gets to the satellite, it gets downlinked over KA. There's no onboard switching or anything like that. They just take the UHF and treat it as baseband and modulated onto KA, basically. So down it comes to the radio access facility, and magic happens, and then it goes back up over KA band to the same or a different satellite, and then back down again to another MUOS terminal. This is DoD's play at using commercial cellular technology to provide mobile subscriber services with satellite. So problem is, MUOS is brand spanking new, and there's not very many terminals that are available, and they're quite expensive. So this is the sort of thing we'd like to do. Implement the wideband CDMA-based PHY of MUOS in a lab using GNU radio, and see if we can interoperate with a blessed, signed off MUOS rig. Here's another problem we're facing right now. The Advanced Wireless Services 3 auction, which you heard some about, I think on Monday if you were here, or maybe it was Tuesday. President's Council of Advisors recommended some things in order to free up 500 megahertz of spectrum for consumer wideband and so on. Problem is, there are a lot of legacy government users in some of that spectrum. Some of them are going to have to move, for which they're getting a big payoff from the auction proceeds that greatly exceeded the wildest dreams of the pundits before the auction. All their legacy government systems are going to remain there. And so, we saw a presentation Monday or Tuesday on, cognitive radio sorts of ways of allowing continued coexistence. So anyway, we've got these things running around the 1700 megahertz band, where we need to see how much damage does LTE do to the incumbents, how much damage do the incumbents do to LTE, and how can we mitigate that. So the sort of thing that we're working on is, since some of the incumbent systems are hard to access, either because they're double super secret and they won't let us touch them, or because there's only a finite number of them and they're all in service and they're radars that were built in the 1950s, and you're not going to take one of them offline and drag it to a lab so that you can do coexistence testing. Well, maybe we can use GNU radio to emulate some of these, and then we can just do a parameter sweep, right? Set it up as a continuous emitter, set it up intermittent. When it's intermittent, sweep through a range of duty cycles, sweep through a range of periods, change the modulation bandwidth based upon what we know about LTE, and see how much mutual interference there is there. So this is the first thing with which I really want to ask for your help. Air Force understands it needs a waveform development environment, and it needs it for a couple of things. First off, the testers want to be able to implement waveforms better, faster, cheaper. And then the developers want to be able to specify waveforms better, faster, cheaper. Those are two separate problems, right? The folks out at the Benefield Anechoic facility, they just want to pump RF into their chamber. And they want to pump like 1,000 signals at once into that chamber, all orchestrated with dynamic modulations and Doppler and other impairments and things like that. And right now, their process is very slow. They come up with a waveform that they want to emit, and they go to a contractor who built them a big honking arbitrary waveform generator 15 years ago, and it was really, really good 15 years ago. I'm impressed by what they accomplished with the technology that was available at the time. But it was 15 years ago, right? And so every time they need a new waveform, they got to go back to the guys who built the AWG and understand the hardware very intimately in order to come up with new, IP to go into the FPGAs to implement the new waveform. They'd like to close that loop faster, right? On the other hand, the waveform developers, they need a way of specifying a waveform better, faster, cheaper, where there's some desirable properties that they want a waveform to have, and then starting from these first principles of what they want the waveform to have, what does the waveform need to look like? Now, I want to distinguish between a waveform description language and a radio description language, right? You might say GRC is a radio description language, right? Or GNU radio is a radio description language. It describes an algorithmic implementation of a waveform. But for any given waveform, there may be many different algorithmic approaches to generating it or to demodulating it. I'm trying to keep an eye on time here, and my phone keeps... Oh, wait, it's still got plenty of time. All right, so for instance, when I was a kid, I had a Gonset Communicator 2 2-meter AM rig. Nobody was on 2 meter AM even that long ago when I was a kid. They were on 2 meter FM, right? Well, I couldn't afford a 2 meter FM, right? So I couldn't talk to anybody, but I could tune the local repeater. And I don't know how many of you know what slope detection is, but when you consider the filter skirts of the audio filter, all I had to do was offset tune the downlink carrier frequency of the repeater. And so as the frequency varied of the FM waveform, I got a different amplitude response out of my filter skirts. My AM ring, I could listen to the FM guys, right? So a radio description language would describe an AM receiver or an FM receiver, but a waveform description language would describe the intrinsic properties of the waveform itself, not any particular procedure for generating it or demodulating it. So we also need to be able to then, once we have a description of a waveform, get rapidly from a waveform description to an implementation. And typically a lot of this work starts in MATLAB, but more and more all of it needs to end in an FPGA. So obviously RF knock is of great interest, and one of my coworkers has been there all day, and I wish I could have been with him, but. All right, so a WDL, this is what we need. Something that will reduce the ambiguities inherent in natural language specifications. I mean, we've all plowed through these specification documents, right? They're 300 pages long, and after 6 months, you don't know any more than you did when you started. So a lot of people have tried to create a waveform description language, and as far as I know, all of them so far have failed. I've got some thoughts after looking at the problem that I'll throw out there. First off, I think you're going to need multiple declarative representations marked up with links. Now, first off, what do I mean by declarative representation? The computer science guys, all three of you out there know what this is. But for the double E's, right? Procedural programming languages say, do this, then do that, then do the other thing. Those are, procedural or imperative. A declarative programming language just specifies what you want and allows the compiler or the interpreter or the runtime or whatever to figure out how to give it to you. And the classic declarative programming language years and years ago was Prolog, right? So if we can declare that we want a bandwidth of, say, 5 kilohertz and not say how to get that 5 kilohertz, and then declare that we want, this, that, or the other thing, then that would be a way of describing a waveform as opposed to describing a procedure to generate a waveform. Right? Why do I say we need multiple declarative representations? Well, obviously, sometimes we look at timing diagrams, sometimes we look at oscilloscope traces, and sometimes we look at spectral masks and spectrum analyzers, right? So you need to be able to look at it more than one way, but then you may need to be able to cross-link these more than one ways, like when we're in this part of the superframe, the spectrum ought to look like this. And when we're in this other part of the superframe, the spectrum ought to look like that, right? Because maybe early in this superframe, we've got a beacon that wants to go out with some simple modulation like BPSK that everybody's going to be able to demodulate even when they're out on the edges of the cell. Whereas then when we move into the superframe and we know that we're talking to somebody close in, we may want to go to 64 clam or something, and the spectrum's going to look different. So some things that may be helpful are some of these XML things. There was a thing called the spectral mask markup language that DoD paid for 20 years ago, which as far as I know nobody uses. And then somehow we're going to need a joint time frequency description, and I think we need to shoehorn that into the XML world. And again, for the computer science guys, I think we need reflective predicates. We may want probabilistic graph grammars. And so I dummied up something that maybe a WDL could look like this. We got a waveform, and it uses an XML namespace of X-Link so that we can use this X-Link construct. We've got a thing called a modulator. It's of type resource, and it's got a label mod. We've got a spectrum, and it's of type locator, and it's got a label transmit IF. And then we've got a time trace, and it's also a locator, and it's got a label of pilot sequence. And then we've got IF out, which is an X-Link, and is of type arc. If you think of graphs, right, with vertices and edges, or sometimes we call them nodes and arcs. Well, it's an arc, and it connects the thing to another thing. And this particular arc connects the thing with the label mod, our modulator resource, to the thing labeled transmit IF, our spectrum locator. And then we've got a subcarrier modulation, which is also an ARC, and it runs from the transmit IF to the pilot sequence. Now, I am not connecting the blocks in a GRC or GNU radio flow graph, right? I'm connecting different descriptions of aspects of a waveform, saying that when we're, let's see, that the modulator should have a spectrum that looks like this, and it should have a time trace that looks like that. Now, I'm waving my hands, okay? This thing doesn't exist. This is an idea of what a waveform description language might look like. And so the first thing I'm doing here today is making an outreach to the community and saying, help. So here's a long laundry list of other things that would be really helpful. And as the disclaimer on the first page said, I don't speak for DoD, I don't even speak for the Air Force. I'm describing some things that I happen to be aware of that are mostly going on within the Air Force. Mostly they're in Rome and other organizations that they serve. We need adaptive fast frequency hopping. And although historically that's been of interest pretty much only to the military, if you think about LTE's uplink, which is not OFDM, but single carrier FDMA, and if you think about the fact that the resource grid can be updated dynamically as often as once every millisecond, well, if you do update it dynamically once every millisecond, that's a 1,000 hops per second frequency hopper. We need fast, reliable transmit-receive switching, which the E300 series may help us do with those discrete outputs. We need better FPGA support, and we've got high hopes for RF NOC, which is why my coworker is downstairs. A MAC layer has been a perennial desideratum in this community. There's this new term that they're bandying about in Rome, SDRF, as opposed to SDR. And the idea is just that in the old days, COM was this narrowband thing, but it did very sophisticated processing. Whereas radar was this wideband thing, but it did, relatively speaking, simpler processing. Well, as A to Ds and D to As get faster and wider, and DSP gets better and better, these are kind of converging. And so wouldn't it be nice if we could use a single underlying technology base to do our COM, to do our radar, to do our EW, etc., all in one big happy framework. And one of the things that this allows is, well, blank your COM every time the radar sweeps by. If any of you have ever tried to use your cell phones at the Naval Research Labs, you know what I mean. So we need power amplifier control because, again, we pretend that these SDRs are radios every time we talk to the FCC, right? Oh, this is test equipment. But when we want to actually use it as a radio, we need more than, 10 dBm. We need a WDL. And another thing we need that I've been told may not be politically acceptable in this community is we need federation with other things. We need federation with competitive things. We saw in the previous presentation MATLAB being called directly from the C++ blocks, right? That's great. I'm going to take that home and use it. We also need to federate with LabVIEW, right? Because LabVIEW is good at what LabVIEw is good at. It's good at running a lab, right? At orchestrating a whole suite of laboratory instruments. And so we'd really like to be able to say, oh, because I just saw this thing on my logic analyzer and this other thing on my spectrum analyzer, I now want to trigger my software-defined radio to emit this waveform, for instance. And that's going to require, cats sleeping with dogs. All right, so for those of you who are core or core wannabe developers of GNU Radio, we're talking about hosting a hack type stuff there. So I wear a bunch of hats. The one that I'm wearing today, in my pointy-haired boss outfit, is this outfit, AX Enterprise, which is a women-owned small business in upstate New York. But I also do some work for Syracuse University and have my own company and so on. Anyway, SU has this really great, all right, I'm running out of time. Come on, go away. SU has this Mineral Conference Center up in the Adirondacks, and it's really nice. It's a great place to have a conference. There's almost no connectivity. Yeah, they've got an internet connection and they've got Wi-Fi, but it ain't much. You go there to think and to work locally and to talk with the small group of people that you're with. You don't go there to be, super connected. And then the Griffiths Institute there, the former Griffiths Air Force Base, they've got much better connected facilities, but not the beautiful venue. And then there's my lab. We've got an anechoic chamber, and we've got great Italian food and the Serenade Brewery. So if any of these work, we can do something. All right, so this is the end of the approved presentation. The slides that follow, I can't put on the website because they're not approved, but they talk a little bit more about some other stuff we're doing. There's this thing called New Air. It's one of the 6 test sites that the FAA has approved for trying to figure out how to integrate UAVs into what's called the National Airspace System. The NAS is that airspace that the FAA controls. Everything above 18,000 feet, everything anywhere near an airport, everything anywhere near a major city, everything anywhere near a defense installation or a nuclear power plant or whatever, right? So the point is how we safely share the space, and we're going to have 3 completely different types of entities in this space. We're going to have manned aircraft, we're going to have human remotely piloted aircraft, so still a human, but his butt's not in a seat on the plane. And then we're going to have autonomous craft, or initially semi-autonomous and ultimately fully autonomous. And these things, I mean, they're not going to work the same way, right? A UAV is going to do something that a human pilot would never do, and all the human pilots went through the same kind of training, and so they all expect all the other aircraft to do the same sorts of things that they would do. And then when this UAV does something different, it's going to cause a collision, right? A human is going to do something that no self-respecting artificial intelligence would ever do, and it's going to freak out the fully autonomous craft. So we need to deal with that. Anyway, that's the old Griffiths runway, which is now the Griffiths International Airport, and we get to fly in that triangle, and we also get to fly in a big honking area in the Adirondack Mountains north of here. And we're having some industry days in September at the Turning Stone Casino, which is run by our local Oneida Indian Nation. This is the data link that the RTCA is looking at using to deal with this. So I've got a bunch. Well, actually, some of this I will be able to give you to put on the website because it's got nothing to do with my Air Force work, so they don't have to bless it. Anyway, there's this control and non-payload communications data link that is currently in review. And it's initially for what's called ground-based detect and avoid, which used to be called ground-based sense and avoid. Later on, they'll worry about airborne sensors. Initially, it's only going to use terrestrial L-band communications for air-to-ground and ground-to-air links. So aircraft are not going to be talking directly to aircraft. Aircraft are only going to be talking to the ground, right? Later on, they'll use SATCOM, and still later, they'll start thinking about air-to-air links. The standard is only to avoid mutual interference, to make sure that Raytheon's aircraft radio doesn't interfere with BAE's aircraft radio, but each of them needs to talk to a different ground system because there's not even any attempt at making an interoperable waveform. You're the one that doesn't cause mutual interference. And then here's the thing that really scares the heck out of me. Almost all of the security that they're talking about is IPsec at layer 3 and a little bit of logical link control security. They explicitly are not doing 5-layer security. Right? I'm really, really concerned about jamming of these air-ground and ground-to-air links as the density of air traffic increases. I've got some opinions, not that anybody asked. Right now, the traditional people are all in this top-down command and control mentality, and the controller will tell you to do this. Meanwhile, all us kids are all flying stuff around, like, cool, we're going to put this neural network on there, and it's going to fly the thing, right? And, oh, it did something I didn't expect, which is great for us as neural network researchers, but really sucks if you're an FAA guy. In between, there's this concept of network autonomy, where you've got things that are in fact autonomous, but they're not just flying around chaotic and uncoordinated doing their own thing. They're at least communicating with each other. And if I were trying to cause mayhem right now, I'd go out and I'd buy a bunch of little quadrotors at under $50 each, and I send a bunch of my friends to airports and military runways all over the country, and as jet aircraft were taking off and landing, I would fly them into the engine nacelles, and 5 engines. And at $50 a whack, I would take out $50 million aircraft, okay? We may need RF cow catchers. Everybody remember what a cow catcher was on the front of the train, right? Swept the cow aside, if you got too close to the front of the train, we may need them for engine nacelles. And I'm not so much thinking mechanical ones, I'm thinking RF ones that'll make sure that anything that's got any kind of C2 data link to it that gets anywhere near the engine nacelle, that C2 data link is jammed, so the guy who's trying to fly into the engine can't. So these are some of the interesting and obviously important problems on which we're working. Now, I just got a couple more of these, and just use them when you need to. So, I've talked a little bit about RF vulnerabilities to UAVs, but UAVs also present vulnerabilities to RF systems, right? This was a recent report. They just put a Zigbee transceiver on a UAV and flown around in Austin, and in 18 minutes they found 1,600 devices, most of which had no security at all in their design, and even fewer, if they had security in their design, didn't have the security turned on, right? So here's the thing with UAVs, they can put antenna apertures where you didn't expect them. You had this big honking building with security guards in the middle of a big honking campus with a fence around it, and at night, somebody takes this little quadcopter that costs him under $1,000, and he flies it in and sets it down on top of the flat roof building. And now, all of a sudden, you're within 100 feet of that 5 gigahertz Wi-Fi access point, and you thought, 5 gigahertz doesn't propagate. I don't need to worry about this. Oops. And there are some enterprising folks who are equipping UAVs specifically for wireless surveys and intrusions. This was on DEFCON a couple of weeks ago. Yeah, I just got 2 slides left. All right, so in my other hat, my own little company, I'm doing this stuff with Syracuse University to try to create remotely testable jails for software. You know, a virtualization framework where the different VMs are really, really strongly isolated, and that's been formally verified and penetration tested, and it's all going to be released as open source so that you can formally re-verify it yourself if you don't trust me, which you shouldn't. And the idea is to be able to have these large, complex systems where we can prove certain trust properties about the system as a whole, even though we can't prove anything about that Windows VM that's full of bloatware and probably malware. Okay, but we can prove something about this, you know, stripped down, thin station Linux that's in another VM on top of our minimized network computing base. Maybe we can get FCC type acceptance of SDR if we run our new radio code in a jail where we can be sure that it's not going to be starved of access to the hardware resources, and it's not going to have any capability leaks to any other VMs, etc. I mean, I would think this is a big issue for our community. And I got this other thing to do a pub subquery DDS for tactical environments, which means radio links that are, intermittent and so on and so forth. It was designed at the higher layers to be robust to port variable quality wireless links, so I want to run it over to the radio as soon as it's a little more mature. By the way, for those of you who are paranoid like me, what it does is location-based information delivery without location tracking. And if this is not a trust me, we don't use it, this is a we never learned it in the first place, right? We never even know where you are, but we deliver the information to you based on your location anyway. So here's the concluding summary. I got a couple of crazy ideas that are enabled by the work that I just described. I'm actually a computational intelligence guy. My PhD work, as I mentioned, was applying information theory to evolutionary computation and machine learning. I want to use genetic programming to evolve comm protocols and evolve waveforms. And I'd really like to see spectrum options. I mean, if you haven't read Ronald Cozy's The FCC, and then his more recent paper, by the way, he died 2 years ago, you need to read it. Even engineers, okay, need to read Cozy's paper on the FCC to understand spectrum options. I'd love to do real-time spectrum auctions, and maybe use Bitcoin to pay. Some less crazy work that the lab would probably fund soon if you proposed it. There's a thing called the BSI, the Bridging Systems Interface. This allows cop radios to talk to fireman radios, to talk to whoever else radios, not over the air, but at a base station where you've got a radio of each type, and you turn it all into SIP, and you do voice over IP stuff according to this profile. SCMML coming out of the IEEE Skyspan working group, that might be a good part for a waveform description language. And we really would like to see some fast frequency hopping. Now, there's 2 senses of fast. First, I'd like to move the LO so that the whole A to D conversion band or D to A conversion band is moving. And I'd like to do that at least at Bluetooth rates. And then I'd also like to hop digitally within the conversion bandwidth several orders of magnitude faster than that. So GNU radio is good for all this stuff. A wider community would help, and this whole talk really was just basically an outreach to those of you who don't already do DoD work and who don't have any kind of ethical issue with it and might be willing to consider it. If you haven't done it before, it's easier than you probably think, and they have some really cool facilities, and if you don't know where to start, talk to me. Thank you.
we have a few minutes for questions. Are there any questions for Stu? Yes, let me.
So you talked a little bit about needing to federate. You didn't bring up the word Redhawk, though.
Oh, so Redhawk, to my mind, is a natural, and I guess it was just a PowerPoint emission on my part. We don't really think of it so much as a waveform development environment as a waveform deployment environment. And afterwards, if you want to convince me I'm wrong, by all means.
Further questions? No? All right.
Thank you
so
all.
much, Stu.